So we're going to take what we understand about a capacitor and we're going to go another step. So remember that we have C equals to our capacitance is equal to the dielectric constant times the area of overlap over the distance of separation. Now, what is the dielectric constant? Well, the dielectric constant represents the kind of insulator that we have in here. It could be air, it could be plastic, it could be something that doesn't allow electrons to flow freely. There's no free flowing electrons in there. And our area of overlap is how these two plates overlap one another. You could have them offset and thus they're not overlapped as well. And thus the capacitance will suffer. So you can look, there's a direct relationship between the proportionality here. It's directly proportional to the area of overlap. That is, the capacitance is directly proportional to the area of overlap. And then we're just going to divide that by the distance of separation. And it's inversely proportional. So that means the greater the distance, the greater these plates are apart, the lower the capacitance will be. So if we reduce the distance of separation, the greater the capacitance will be. It's basically what we're saying. And we're also saying that instead of drawing this big thing each time, we're just going to symbolically represent this idea with this idea. So this idea will be symbolically represented with this idea. So let's go ahead and utilize that. So we basically have this, and this is going to represent a capacitor, some capacitors C. And capacitance is measured in farads. So just so you know that, it's going to be measured in farads. And I'm putting the F there, but it represents this, all right, a farad. And it's named after, I believe his name is Michael Faraday. So let's continue right on. So let's look at C equals to kappa times the area of overlap over D. We can manipulate the value of capacitance in a circuit, which is what you want to do. You want to be able to control what kind of value of capacitance you're going to put into a circuit so that you can get the kind of output that you want to have. So you have input going into a circuit, and then you're going to get an output. So here we go. We have A here. And how do we manipulate A? Well, we know that if we increase the area of A, we will increase capacitance. So if we increase area, we're going to increase capacitance. So the way we increase the area is by putting capacitors in parallel, like so. So you can have C1 here and then C2, and they end up being additive. So you end up with C, the total capacitance for this kind of circuit, if this is plus on this side and minus on this side. The total capacitance is just going to be C1 plus C2. That's pretty much it. Now, we can derive these from first principles, and I probably will do them in class. And so when I say first principles, it's the conservation of energy. But I really want to just talk to you quickly about how to represent these things. So what if we wanted to reduce the capacitance in a circuit? We can increase the distance of separation, and thus the capacitance would reduce. So how do we do that? Well, we just put capacitors in series. C1, C2, okay? And now that they're in series, you'll notice that, well, you may not notice it, but we have a representation for that. That's going to be CT, 1 over CT is equal to 1 over C1 plus 1 over C2. So we have not only symbolic representations, but we also have mathematical representations. So the idea is this: if you know C1 is equal to C2 is equal to 1,000 farads, this implies that the total capacitance for capacitors in parallel is just 2,000. Okay? If you know that C1 is equal to C2 is equal to 1,000, and you have capacitors in series, we know, and you can do this calculation, that CT, I'm just going to put an S down here and a P right here to differentiate between parallel and series, is going to be 500 farads. So it basically cuts it in half. All right? Why is this important? Well, essentially, we make capacitors. Manufacturers make capacitors, and they have certain ones that they make. But let's say you have a circuit that needs a specific kind of capacitor. Well, based on different capacitor configurations, you can build the capacitor that you want. All right, so it might be best that you have one capacitor that meets your specifications, but if you don't have that and resources don't allow you, then you just go to Radio Shack, pick up a bag of capacitors, make sure that they have the ones that you need based on your theoretical calculations, and then put that into your circuit, and you'll have a capacitor. Okay? There might be some other things that go along with that, but you'll have the capacitor that you need. So that is where, this is what we want to derive, and we're going to derive this in just a second.